Hello, welcome back. So in the last module, we looked at the kinetics occurring in the main hydration peak and the mechanism for that. And before going to look on what happens in the longer term, in this module, we're going to look at what's called the filler effect. This is the impact that supplementary cementitious materials have on the hydration, not because they are themselves reacting, but because of their physical presence in the mixture. So during the first day or so, most supplementary materials are not reacting. Their physical presence affects the hydration of the clinker, and this is what we mean by the filler effect. So we can see that by looking at this data here coming from different mixtures. So the first one in black is the reference cement, and then we took this reference cement and we mixed it either with 40% quartz, as shown in blue here, or with 40% slag, as is shown in orange here. And the slag and the quartz were chosen that they had about the same particle size distribution, as you can see by these images here. So we can see in the first day that when we take these calorimetry curves and we normalize them by the cement content, so that's very important. This is just as if there was 100 grams of cement, reference cement in all cases. You can see that the reaction of that cement is enhanced in both cases. It's enhanced by the quartz, it's enhanced by the slag, and pretty much in the same way in the two cases, which really emphasizes that it's a purely physical effect because quartz is non-reactive. We've checked that the amount of reaction even at 28 days is barely measurable. After the first day or so, we can see now that the slag reactivity starts to be higher, and this is indicating that this is actually the slag itself reacting. So over here we have the filler effect, here we have later on the chemical reaction. Now when we look into the micrograph, why did we do this? The reason we did this was that most people have proposed that this filler effect is coming from the extra surface providing extra nucleation sites for CSH. And when we look in the SEM, this seems to be the case. So this was a system of cement and quartz. They're hydrating together. So the pictures are taken in exactly the same sample. And here we see a cement grain. You can see these little nuclei forming on the surface, and then you can see these needles of CSH forming. And here we see the quartz grains. It looks really the same. We've got the CSH nuclei on the surface from very early times, and then from those little nuclei, the CSH is forming. So the hypothesis seems to be correct. However, when we look at it now more quantitatively, it's not so good. So this graph here shows how the slope, that's to say the slope of that acceleration part, varies with the amount of surface. Okay, so this is the reference Portland cement down here. Okay, and if we increase the amount of surface by 2 times, so here we've got twice the amount of surface, but we've only increased that acceleration slope by 20%. So if it was just the fact we had extra surface, this doesn't add up, because we would expect it to be twice as much there, which is clearly not the case. So what can we suppose? Well, if we now go back to look at mortars versus cement paste, so cement paste where we just have water and cement grains versus mortars where we have water, cement grains and sand, we can see a similar acceleration or an increase of that acceleration slope. And if we look at the pictures in the SEM, we can see that here we've got just the plain cement, we've got some bits of CSH, but also some bits of quite smooth surface. Here in the mortar, we've got a much more confused picture with many more small nuclei on the surface of the cement grains, just by the presence of those large sand grains. And this picture here looks very, very similar to what we see in the quartz cement system. So what we can suppose is that in the mortar system, the presence of the sand grains during the mixing phase is knocking those little nuclei off the surface. It's redistributing these nuclei through the space, and by that shearing effect and redistributing the nuclei, then we're getting more nuclei on the surface, and we then getting the acceleration effect. And again, we can test this quantitatively. So now we can look at a variety of different systems, of different quartzes with slag and with fly ash, and we can plot all these results against the relative to the different shear rate between the particles. And we can see as the shearing rate is going up, the slope value is going up. So this is now our idea of why we get this physical filler effect. And as we see on this graph, the slag and the fly ash really act in very much the same way as we get with the quartz. However, if we now go to the effect with limestone, we see that with limestone we get a very different reaction. We're getting much, much more accelerating effect from the limestone, even when we have the same shear rates. And now if we go in the SEM and look at this effect, we can see that on the limestone grains, we've got this very, very dense covering of nuclei, much, much denser than we have for the cement grains. And what it seems is that the low but measurable dissolution of the limestone grains is increasing the calcium concentration close to the surface, and that helps to stimulate the nucleation of CSH. And once we form that much more dense number of nuclei here, then these grow as this denser clusters of needles. So this really emphasizes how limestone can have this very particular effect. So if we just summarize that module here, although they are inert, these supplementary cementitious materials do have a very significant effect on the nucleation growth of CSH. We have a small increase in nucleation sites due to high shearing conditions, but some surfaces, for example calcite, also favor the nucleation of CSH and change the growth pattern. So now we've looked at this main hydration peak and what happens with supplementary cementitious materials. Next time we'll look at the longer term hydration. Thank you.